Okay. So, worksheets 16 through 18 are due on the 16th. That is next week, Thursday. Homework number 2 is also due on the 16th, again, next week, Thursday. And exam number 2 on chapters 16 through 18 will be on the 16th. Additionally, because it's coming up, your project for your semester project is due on the 21st. That's 2 weeks from today. Just reminding you, because it's coming up. You can submit it whenever. Project topics are first come, first serve. So if someone else has picked your topic before you, you'll have to pick a new one. I'll respond. There's a list of suggested topics on Brightspace that you can choose from, but you are not limited to those. You can make up a topic if you want. So we were talking about minerals. Oops. And sign in on the sign-in sheet. We were talking about minerals. So continuing with the properties of minerals, we can talk about the strength of minerals. There's a few different ways you can measure strength. The one people talk about a lot is hardness, which is the ability of a mineral to resist scratching or abrasion. So the way it is in the field tested is you compare. So basically, if something is harder than something else, it will scratch it. So if I have like a nail, and a copper penny, the nail will scratch the penny because it is harder than the penny. But if I have a penny and my fingernail is not as hard as the penny, so the penny will scratch my fingernail. So that's how we can set up a relative scale. So the more commonly used scale is what's known as the Mohs hardness scale. And it is a relative scale based on comparing the hardness of various objects. You can measure it absolutely by basically pushing a very hard thing into a surface with a certain amount of force and measuring how much you actually push into the surface. That's how you get an actual measurement for hardness. There are machines to do this. This is not commonly done with minerals. It's commonly done with metals, because for a number of types of metals, you're interested in the way you process the metal with heating and cooling and stuff can change its hardness. So you're interested in the granular detail. So it's not so much an identification tool there. But hardness is not like absolute strength. Lots of hard things are easy to break, but they don't make a little deformation, they just crack. So lots of hard things are brittle. So if they start to break, that break transmits. They're not durable often. So hardness is the ability to resist scratching or abrasion. Cleavage is the tendency to break along planes of weak bonding, the way that things break. You get flat surfaces. Fracture is when you don't have cleavage. It's when you have a more random pattern of breakage. With fracture, you can have irregular breakage, or you can have these, you sometimes have these like shell-shaped curves that form. If you've ever seen like a piece of flint break, it forms these like curved indentations, almost. And then tenacity is the resistance to cutting, breaking, bending, and deformation. It's a measure of toughness, basically. And that's different than hardness. So lots of things that are very hard aren't very tough. And often there's an exchange where the harder a thing is, the less tough it is. You can't take as much beating. Another important thing you study in minerals is specific density, specific gravity, the density of the material, because that's going to be different for different minerals. So you can use it to identify minerals. And this can be measured by, measuring the mass and the volume of the mineral sample. You can also kind of drop it in water and see how fast it sinks, amusingly. I hit the wrong button. So, for hardness, as I mentioned, there's the Mohs scale, which is the common scale for hardness. It goes from the softest mineral, talc, up to the hardest mineral, diamond. But on an absolute hardness scale, I don't know which hardness scale they're using here. It's not one I'm familiar with, because the ones I'm familiar with would have bigger numbers for these. But on an absolute hardness scale, it looks something like this. And you'll see that there's this relationship, every position on the Mohs scale is higher than the one before it. But, like, especially at the end, you see there's a really big jump at the end. But it's totally fine that there's nothing in between 9 and 10, because there just isn't much in between corundum and diamond hardness. Not much out there is harder than corundum and softer than diamond. So you don't need much in the middle. So this is it's a relative hardness scale. It's an organizational tool. And it works for actually figuring out the hardness of things. So here is a short video about mineral hardness.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe mineral hardness, where it comes from, how to measure it, and why it's useful in identifying minerals.
There.
So here's an example of a mineral. We can see that it's sort of transparent and light colored. Doesn't appear to have a metallic luster, but how can we identify it? We've got to look at the physical properties of this mineral, and one of the physical properties that's most useful is hardness. It's important to realize that hardness is not mineral strength. It is merely resistance to being scratched. So if you want to figure out a mineral's hardness, you've got to try to scratch it. What should you scratch it with? Whatever's handy. There are certain tools that are common everyday objects that have a known hardness that are useful in assessing mineral hardness. One of them is a penny. So what you do is you simply take your penny, you try and scratch the mineral with it, and once you've done that, if you succeeded in scratching the mineral, as we did here, leaving behind little gouges in the mineral face, then that means that the penny has got to be harder than the mineral. So the mineral is therefore softer than the penny. This is the basic idea behind the Mohs scale of hardness. This is a relative hardness scale developed by a mineralogist named Friedrich Mohs, and it ranges from the softest known mineral, talc, all the way up to the hardest known mineral, diamond. There's 8 steps in between those two. Our penny is an example of an object of known hardness. So a penny is a hardness of 3.5. The previous example where we were able to scratch the mineral with our penny means that our mineral must be softer than 3.5. Another object that's often useful is your fingernail. Your fingernail is a 2.5 on the Mohs scale of hardness. A wire nail clocks in at 4.5. A knife blade or a piece of glass is 5.5. And the ceramic streak plate that we use for assessing the color of the powdered form of the mineral, that streak plate is a 6.5. So when you're identifying minerals in a laboratory, you basically want to bracket a mineral's hardness between two of these numbers. So for instance, if it is softer than the streak plate but harder than a piece of glass, that means it's somewhere between a 6.5 and a 5.5 on the Mohs scale of hardness. Now the Mohs scale of hardness, like I said, is a relative scale. It's not actually an absolute scale. So the difference in hardness between, say, talc and gypsum is actually much less than the difference between corundum and diamond. Just the same, the Mohs scale of hardness is really useful, especially for introductory geology students. Here are 6 sample minerals that all could look very similar to one another. The fluorite obviously stands out because it's bright purple, but keep in mind that color can really deceive you when it comes to identifying minerals. So rather than relying on color, let's check the hardness of these different minerals. Calcite will clock in at around a 3 on the Mohs scale of hardness. Dolomite will be about a 3.5. Halite is around a 2.5. Gypsum is around a 2. Fluorite is a 4. And quartz is a 7. Let's slide that fluorite over to the side here and consider it in a little more detail. If fluorite has a hardness of 4, what common everyday objects will scratch it, and which ones will be scratched by it? If you answered that the knife, the wire nail, and the streak plate should all be able to scratch it, since fluorite is a 4, and that fluorite will be able to scratch both a copper penny and your fingernail, then that's the answer I was looking for. Good job. It's exactly that kind of logic that you need to use for assessing mineral hardness. Thanks for your attention. This has been another Smart Figure.
So cleavage is when a mineral breaks along flat surfaces. And cleavage corresponds to the internal crystal structure, because these flat planes, oops, I hit the wrong one, sorry. These flat planes, where it breaks, are lines of weakness. They're directions where the bonds aren't as strong. So like in mica minerals form in sheets that are basically stacked on top of each other. So they have very strong bonds in 2 directions and weak bonds in the 3rd direction. And so they break, separating off sheets in that direction. And that's why you get cleavage in 1 direction. Here we have one that has cleavage in 2 directions. Here we have 2 directions not at 90 degrees angle. Here we have something that has a very stable cubic structure, and so it breaks, it cleaves fairly cleanly in 3 directions at right angles. This is halite. Here is 3 directions not at right angles, calcite. And then fluorite has a more complex structure, so it could actually cleave in 4 directions, and you get these octagonal structures, octahedrons. But there are some other crystal structures that can form as well. So mineral cleavage tells you about which layers, which directions are strong and which are weak in the crystal structure.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe what's going on with mineral cleavage. What's the basic underlying reason that some minerals cleave and other ones don't? And you should be able to describe how to use mineral cleavage to identify different minerals. Here's an interesting phenomenon. This is a crystal of mica, and you can see that this person is actually peeling back a layer from that mica. The mica readily splits into thin little sheets that are transparent and relatively flexible, but the sheets themselves are very hard to break. What's happening here is a classic example of mineral cleavage. On the atomic level, the mica has very strong bonds that hold together the sheets. So between the atoms of the sheets of mica themselves, the bonds are quite strong, but those sheets are held together with relatively weak bonds. So these little red dots that you see here in the middle are relatively weak bonds that are really easy to split. So it's easy to break the little red weak bonds, but it's very difficult to break the blue-colored strong bonds. Not every mineral has cleavage. Some minerals have equal strength bonds in every direction throughout the mineral crystal, and they may break with a fracture. That fracture may be an irregular fracture, as in the example on the left, or a clamshell-shaped conchoidal fracture, as in the example on the right. 2 minerals that break with a conchoidal fracture are quartz and olivine, and you're probably familiar with glass. Glass will also break with a conchoidal fracture. Here's an example of the mineral calcite. Calcite has 3 planes of cleavage that intersect at non-90 degree angles. So in this picture here, there's one plane of cleavage which defines the front face of the sample, but it also defines the back face of the sample. So don't confuse that with 2 different orientations. That's only one plane of cleavage, one orientation. You could also have a plane of cleavage over here on the left side, defining that face there, and you can see that that same plane is repeated throughout this mineral crystal and ends up defining the back right side as well. So that's a second plane of cleavage. No matter how many times you see that same orientation repeated, it's only one orientation. And lastly, of course, there's the plane of cleavage that defines the upper surface of this sample. It also defines the lower surface. And if you hit this sample with a hammer, it'd be very likely to break along that same plane of cleavage running throughout the mineral crystal. Here's a summary diagram showing some of the different situations that we can get when it comes to cleavage. The example with the muscovite mica that we looked at the beginning of the video is in the upper left. It's only got one plane of cleavage, so it splits into thin sheets, but only in one direction. Feldspars are an example of a mineral that has 2 planes of cleavage, and those 2 planes are at a 90 degree angle, or a right angle, relative to one another. There are also minerals that have 2 planes of cleavage, but they do not intersect at a right angle. Hornblende, which is an amphibole, is an example of that. So there, the angle between the 2 planes is around 120 degrees. Here's an example in the lower left where we've got 3 planes of cleavage. They're intersecting at 90 degree angles, which means that the mineral will break into cubes and pieces of cubes. The example mineral there is halite, or table salt. In the lower center, we've got calcite, that example we just looked at, 3 planes of cleavage that are not at 90 degree angles. The actual angle is 75 degrees, but the key thing to recognize here is that it's either 90 degrees or it's not. That's going to be most useful for you when you're identifying minerals in the lab. Lastly, here's a more complex example, a mineral that has 4 planes of cleavage, and that's fluorite. Here's a review question for you. This is a mineral that we looked at when we were talking about luster in the mineral color video. This is galena. How many planes of cleavage do you see here on this mineral? If you answered 3, that's correct. So you can see one plane of cleavage that's forming all the little fractures that are vertical in this sample. There's another plane of cleavage that's forming the little fractures that are horizontal in this sample. And then there's a third plane of cleavage which is basically going from the front towards the back of this sample. And so those are all at 90 degrees to one another. And so galena breaks into cubes and pieces of cubes. In terms of cleavage, it's just like halite, the example that we looked at just a few minutes ago. Thank you very much for your attention. This has been another Smart Figure.
So cleavage and how things break gives you insight into the crystal structure of the mineral. Some other properties that are distinctive. Sometimes, this is a thing that geologists do that very, very few other scientists do, is that taste. Also, like how it feels on your tongue is something they use sometimes. Because certain things will be more porous than others, and you can identify them that way. So some minerals can be identified from distinctive properties like taste, smell, their elasticity or their malleability, how easily they bend and bounce back, or how easily they deform. Things like double refraction, where certain minerals will take the light in and they'll split it at bend it at 2 angles. That can have some interesting uses. You can actually, there's a thing called the sunstone that uses that fact. And cleavage mentioned before, one of the things you can do with mica that's very useful is because you can make these thin, strong sheets very easily, it was used in a lot of things for diaphragms for like microphones or speakers or pressure gauges and things. Anything you needed a stiff, somewhat flexible diaphragm that wasn't metallic, it got used a lot. So magnetism, oops, what it feels like. And lastly, there's a few minerals that one of the best ways to identify them is to put a drop of dilute hydrochloric acid on them and see if it bubbles. Specifically, calcite is very easy to identify that way because it's calcium carbonate, and when it reacts with hydrochloric acid, the carbonate ions basically turn into carbon dioxide and bubble off, much like vinegar and baking soda. But vinegar is a weaker acid, and baking soda is a bicarbonate. It has two carbonates, so it pumps out even more bubbliness. So when we look at minerals, most rock-forming minerals are made from 8 elements. These are, in order from most common to least common: oxygen. Oxygen is the most common element in the crust. Silicon is number 2. And silicon and oxygen together form the core of the largest group of minerals. So silicon oxides, silicates, form the largest group of minerals. Then aluminum, which is common in many minerals, iron, calcium, sodium, potassium, and magnesium. Those are the most common elements in minerals. So most rock-forming minerals are formed from these 8 elements, mixtures of these 8 elements. There may be small amounts of various impurities. There may be some other things in there, like rubies are aluminum oxide with a tiny bit of chromium, which is not on this list. But the chromium makes it a ruby, it makes it red. And so here's the distribution. The 8 most abundant elements in the Earth's continental crust are oxygen at 46.6%, nearly half, silicon at 27.7%, then iron at 5%, then aluminum at 8.1%, iron at 5%, calcium at 3.6%, sodium at 2.8%, potassium at 2.6%, magnesium at 2.1%, and then everything else is 1.5%. So the most common mineral group is the silicate minerals. These are built up of silicon and oxygen. And silicon and oxygen together form the silicon-oxygen tetrahedron, which is a silicon surrounded by 4 oxygens making a little triangular pyramid. 4 oxygens surrounding a much smaller silicon atom. And this combines with other atoms to form the various silicate structures. The most basic of these is that they can share their oxygens in their corners and form a 3-dimensional lattice, and you get quartz. That's the simplest silicate mineral. So quartz is basic. The formula works out to silicon dioxide because each tetrahedron with 4 oxygens is sharing each of its oxygens with another tetrahedron. So it effectively works out to 2 oxygens per silicon. And they're arranged in groups based on how the tetrahedra bond. Because different bonding structures in the tetrahedra lead to different crystal structures, which lead to different minerals. And you can have other things mixed in with these tetrahedra. So here's the silicon-oxygen tetrahedron. We have a silicon in the middle, surrounded by 4 oxygens. This is an expanded view, so you can sort of see what's going on. Silicon with 4 oxygens. Silicon is +4, each oxygen is -2, charge-wise, effectively. And so this can share oxygens with nearby tetrahedrons and work to a balanced state of silicon dioxide, or you can mix in other ions and balance it that way, and then it might not share as many. So silicate minerals can have just individual tetrahedra floating around. So these are things like olivine. So individual silicate tetrahedra with magnesium and iron ions mixed in. That creates olivine. If they're long chains, so olivine will have no cleavage. If they're long chains, you'll get two planes at 90 degrees. This is the pyroxene group that's got magnesium, iron, calcium, and sodium with aluminum and silicon and oxygen. Lots of stuff in there. You can have amphiboles group, which are these double chains, and you get two planes at 60 and 120 degrees of cleavage. This has calcium, iron, and magnesium, silicon and oxygen, and then OH. So that's like a hydroxide. And then there's the micas. There's the biotite mica, which has iron and magnesium in it, and the muscovite mica, which is more potassium and aluminum. With the silicas, they also have OHs in there. And these form sheets. It's potassium and aluminum, but this also has iron and magnesium, while this one doesn't. And then the feldspars got, there's potassium feldspar with potassium, aluminum, and silicon and oxygen, three-dimensional structure, has two planes at 90 degrees, and plagioclase, which is calcium and sodium with your aluminum and silicon, that also is a feldspar, and then quartz, which is just silicon and oxygen. So these are the silicate minerals, and they are classified by their structures, how the silicon tetrahedron is organized within the minerals.
This is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the relative importance and basic structural similarities of the most common group of minerals in the Earth's crust, the silicate minerals. If you look at this image, you'll see a rock that's actually one of the most common rocks in Earth. This is peridotite. It's an igneous rock that's very common in the Earth's mantle. It's made out of a mineral called olivine, mostly, with a little bit of the mineral pyroxene in it as well. Both of these minerals are silicate minerals, and so silicate minerals make up a huge portion of the mantle. They also make up a huge portion of the crust. Here's a pie chart showing the relative proportions of different elements in the crust. I'm not going to go into this in a lot of detail, but what I want to call your attention to is that the two most common elements in Earth's crust are silicon at around 28% and oxygen at around 47%. You can see that other important elements are aluminum and calcium and so on. But the key thing here is that a huge proportion of the Earth's crust is made out of either silicon or oxygen. And so you would expect minerals that are rich in silicon and oxygen to be very common minerals. Well, you'd be right. The silicate minerals, the ones that have silicon and oxygen in their chemical structure, make up about 92% of the Earth's crust. Non-silicate minerals, in contrast, make up only about 8% of the crust. If we take a look at some of the details there, we see that about half of all minerals in the crust are feldspars of one kind or another, either plagioclase feldspar or potassium feldspar. Other important silicate minerals include quartz, pyroxenes, amphiboles, micas, clays, and a grab bag of other silicates. All silicate minerals have something in common, and that is that they have silica in them. So in general, the chemical formula is SiO2 for silica. What's shown here in these images are SiO4. The reason for that is we're showing the silicon-oxygen tetrahedron. And this is a really key structure in all silicates, whether or not they have lots of oxygen or relatively little oxygen. So you can see here that basically you've got a silicon atom shown in blue surrounded by oxygen atoms, which are the big red atoms. A more expanded view is shown over here on the right, where you can see the silicon atom in the middle, and then it's bonded to these neighboring oxygen atoms, 4 of them in every direction. Those 4 atoms end up defining a 4-sided face around that central silicon atom, and so it basically is like a little pyramid or a 4-sided figure, a tetrahedron. the plural of tetrahedron is tetrahedra, those tetrahedra can be linked to one another in various ways. So some of those ways are illustrated here. You can see that they can be independent tetrahedra. The tetrahedra can be linked together in single chains. The tetrahedra can be linked together in double chains. The tetrahedra can be linked together in big sheet-like structures, or it can be more complicated. Let's take a look first at the independent tetrahedron situation, where you've got these little tetrahedra bonded to other atoms, and these atoms are usually positive ions like magnesium or iron. And this is the case with that green rock I showed you at the beginning. The peridotite, that mineral that makes up most of the peridotite, olivine, is made out of a crystal structure that looks something like this. So that's up here at the top, olivine. You'll see that our single chain silicates are called pyroxenes. Augite is a specific example of a single chain silicate. The double chain silicates are members of the amphibole group. Hornblende is our example mineral there. The sheet silicates are biotite and muscovite. They're both examples of micas. We've seen micas in another smart figure where we talked about mineral cleavage. And then lastly, we've got the more complex three-dimensional networks, and basically these are in two main groups, the feldspars and then quartz. The feldspars are the most common minerals in the Earth's crust. So they occupy together, potassium feldspar and plagioclase feldspar, we're talking about half of the volume of the crust. It's a tremendous volume of the crust. And they come in many different varieties. Some are richer in potassium, some are richer in calcium, some are richer in sodium, but we end up seeing that these minerals are very, very common in Earth's crust. Okay, let's see how much you remember. Here's a hornblende and an augite. What's the silicate structure of these minerals? Remember that hornblende is an example of an amphibole, and augite is an example of a pyroxene. Hopefully what you said is that hornblende is an example of a double-chained silicate structure, while augite is an example of a single-chain silicate structure. Okay, thanks very much for your attention. This concludes another smart figure.
So often the silicates get sort of divided into light silicate minerals and dark silicate minerals. And that's partially because they show up in different places. When we start talking about rocks, we'll find that certain types of rocks are rich in light silicates and other rocks are rich in dark silicates. And the common light silicate minerals are light in color and they're less dense. Oh. So these are things like the feldspar group, which have a three-dimensional network of tetrahedra. This is the most plentiful group of silicate minerals, most plentiful group of minerals out there. Potassium feldspar is feldspar rich in potassium ions. Plagioclase feldspar contains both sodium and calcium ions that can substitute for each other. So potassium feldspar has potassium, plagioclase has sodium and calcium instead. So here's potassium feldspar. Here's a nice crystal of potassium feldspar. It's orthoclase, and this is showing cleavage. And this is, so the specific mineral is orthoclase in this case. Here's a sodium-rich plagioclase. Feldspar, this is albite, and there's a plagioclase feldspar that's showing striations. This is laverite. Laverite. So there's a lot of individual things, but the feldspars is the big group that people talk about. Another light silicate mineral is quartz. This has a three-dimensional network of tetrahedra. It's the second most abundant type of silicate mineral. It's just silicon and oxygen. And quartz comes in lots of different colors, but all those colors come from impurities. Pure quartz is clear, transparent. Doesn't have any color. Now, quartz comes in basically every color of the rainbow. And in fact, there are some out there that contain, I think you can manage to grow a quartz that is like rainbow colored if you were doing it right. But, there are all kinds of crazy things with quartz. A lot of the different colors of quartz have special names, like amethyst. If you've heard of amethyst, that's just purple quartz. So the impurities make different colors. So here are some quartzes: smoky quartz, rose quartz, milky quartz, amethyst. They're all quartz, but they all have different colors and different impurities. Next, we have muscovite, the mica group in the light silicate minerals. These have tetrahedra that are arranged in sheets. They have excellent cleavage. They're quite useful. Micas are useful for when you need a thin, strong sheet of something to act as a diaphragm or go over something. They used to be used in microphones and things all the time. Then we have clay minerals, which have tetrahedra that are also have tetrahedra arranged in sheets. And clay minerals are interesting because they don't form like from magma or from molten rock. Clay minerals form from the chemical weathering of other minerals. Generally, you start with feldspar and it gets chemically transformed into clay minerals. So these are complex minerals that originate through chemical weathering of other minerals, usually feldspars, and they make up clay. So because they're in these sheets, they form these little flat platelets, which allows them to stick together well and form structures. Now, the dark silicate minerals are dark in color. They're heavier. They're denser. And they contain iron and or magnesium, which is why they're dark in color and why they're heavier or denser. So these are things like the olivine group, which has single tetrahedra. It's found in basalts and oceanic crust. It makes up the mantle rocks. So there's a lot more dark silicate minerals in things that form from lava that came from deeper underground. So the closer you get to magma, the hotter the lava was, the more dark silicates you get. And you literally get darker rock. So you can identify the types of rock by the color. Like you get dark lava, you get dark rocks and light rocks. That'll come up in the next chapter. There's also the pyroxene group. These have tetrahedra arranged in chains. Again, they're found in basalts. The amphibole group, these have tetrahedra arranged in double chains. And these are found in many igneous rocks. There is the dark silicate mica. This is biotite mica, which is a dark mica. Again, tetrahedra arranged in sheets. Again, common in many igneous rocks, but these are ones with iron or magnesium in them. Garnet are single tetrahedra. This is found in many metamorphic rocks. Certain types of gemstones are common in metamorphic rocks because they basically recrystallize out of the other minerals. So this is an olivine-rich peridotite. This is the olivine. This is augurite. This is hornblende. These are some common dark silicate minerals. Now, all of the other minerals in the crust are considered non-silicate. Non-silicate minerals are less than 10% of the crust. The most common non-silicate minerals are the carbonates, the oxides, and the sulfides. We'll actually talk about more than that, but and also things that are non-silicates are things like pure elements, like gold and silver, and some gemstones are non-silicates, like diamond, ruby, and sapphire. Diamond is just made of carbon. There's no silicon in there. And ruby and sapphire are made of corundum, which is aluminum oxide. Again, no silicon. Technically, ruby and sapphire fall in the oxides. So, the non-silicate minerals, some of the important non-silicate minerals. They're generally named for the ions that make them up. So they're usually some metal ion and the other thing. So a carbonate have carbonate ions, which is CO3. I think CO3, yeah. Halides have halogen groups in them. So things like chlorine or fluorine, that column of the periodic table. Oxides have oxygen. Sulfides, sulfides have sulfur. Sulfates have a sulfate ion, which is a SO2, or is it SO3 ion? I can never remember the names. And then there are things like native elements. Native elements are things like just gold or copper can just show up. You can have pure elements. So diamond would fall in that category as well. So some examples: carbonates, things like calcium carbonate that makes up limestone, or dolomite, calcium and magnesium carbonate. It's CaCO3. Yeah, let me look on over here where there's more resolution. Yeah, carbonate is CO3, so economically they're used in things like Portland cement and lime. Make up limestone and dolostone and things. The halides are things like that have chlorine, fluorine, or bromine. So some examples are halite, fluorite, sulfite. Halite is table salt, sodium chloride. Fluoride is calcium fluoride, CaF3. That's used in steel making. And sulfite is potassium chloride. It's used as a fertilizer. So this is halite, this is fluorite. The oxides are various things with oxygen. So hematite, it's F2O3. Yeah, I think that's right. That's an ore of iron, it's a pigment. Magnetite is maybe F5O3. It's another iron and oxygen one. F2O3 and F2O4, that's what they are. Corundum is aluminum oxide. It's Al2O3. It's used as a gemstone. It's also used as an abrasive. You've certainly heard of it used as a gemstone. Sapphires, rubies. You may have used it as an abrasive. It's very common as an abrasive, actually. So if you've ever used an emery board, emery is a variety of corundum that's used as an abrasive because it doesn't form big, pretty gems. Also, it's black, so it's not very attractive. And if you've ever used, artificial aluminum oxide is used all the time as an abrasive. Like half the sandpaper out there got corundum on it these days. If you see aluminum oxide sandpaper or aluminum sandpaper, it says something like that. That's corundum on it. So it gets used all the time for that. Ice is an oxide. It's hydrogen oxide. So, the solid form of water. And then there's the sulfides. There's sulfur. So things like galena is lead sulfide. Sulfurite is zinc sulfide. Pyrite is iron sulfide. Copperite is copper iron sulfide. Cinnabar is gorgeous and very toxic because it is mercury sulfide, but it is a gorgeous red. This is also the sulfates are, I guess it's SO3 or is it SO4? 4. It's SO4. Sorry, I can never remember this. These are things like gypsum, which is calcium sulfate with some water packed in. We use it to make drywall. Anhydrite, which is calcium sulfate without the water. Barium sulfide is barite. And then things like native elements. You can get gold, native copper. There's 2 forms of carbon, diamond and graphite. They're both pure carbon, but they have different crystal structures, so they have very different properties. Diamond has 3-dimensional structure, graphite comes in sheets. You can have pure sulfur, pure silver show up. Native, so this is pure sulfur, this is native copper. So the carbonate minerals form in the carbonate ion. CO3A2- bonds with various metal ions like calcium, magnesium, manganese, iron, and others. Calcite is a very common carbonate water. Calcium carbonate. It readily dissolves in acidic water. It's the main component of limestone. Because it readily dissolves in acidic water, it's the main source of caves. Most large cave structures form from water dissolving away calcite. It's the main component of limestone. Limestone dissolves over time, and that forms caves. So here is some calcite. This is a sample of limestone. Oxides. Oxide minerals form from the bonding of oxygen ions with metallic ions. So Fe2O3, so iron oxide, tin oxide, and uranium oxide are all oxide ores for their respective metallic ion. Sulfide minerals form from the bonding of sulfur with various metallic ions. So iron, lead, copper, zinc. So iron sulfide is pyrite. It's commonly called fool's gold. Copper iron sulfide, lead sulfide, and zinc sulfide are all sulfide ores for their respective metallic ion. Lead sulfide, that's galena. So here's uranium dioxide. Here's pyrite, iron sulfide. So minerals are a non-renewable resource. So a renewable resource is something that can be replenished in a relatively short period of time. Things like corn, wind, water, etc. If you can get it back in the scale of a human lifetime, it's renewable, more or less. I mean, we have water supplies that really we're draining faster than we should and things like that, but that's the general idea. Non-renewable are things where Earth has more or less a fixed quantity. Yes, there are processes that are replacing them, but they take such long periods of time, we're using them much faster than they're being replenished. These are things like oil, aluminum, natural gas, coal. So oil, natural gas, and coal, like especially coal, the processes that generated coal just aren't happening anymore. So we can run out. Now, some of these we're not likely to run out. Oil, natural gas, and coal, possibility. Aluminum is really common though. So mineral resource sources. So let's talk about the difference between a mineral resource and an ore deposit. Mineral resources are occurrences of useful minerals that will eventually be extracted. So this is someplace there is stuff that we would like to get that we'll eventually extract. Ores are specifically concentrations of metallic minerals. When we talk about ores, we're talking about ways we get metals. So they're concentrations of minerals containing metals that can be mined at a profit. So whether something is an ore is determined by whether it's profitable to mining. So if the demand for some metal suddenly shoots through the roof, stuff that wasn't an ore can become an ore. And the opposite can also happen. If we stop needing a certain metal anymore, things will stop technically being ore deposits. The ore deposits are concentrations of metallic minerals that can be mined profitably. So the big thing about an ore that defines whether an ore deposit is technically an ore deposit is whether it makes money. So economic factors can change and influence a resource. So here is a copper mine. This is the Bingham Canyon copper mine near Salt Lake City, Utah. It's an enormous hole in the ground. This is a pit mine. They basically just peel off the earth until they reach the mineral, the copper ore, working their way out, basically. Copper mines tend to be like this. Yeah, so that was the end of chapter 2. Any questions about any of the stuff about minerals? So let's save this. And start up chat. Now we wait for the computer. Okay. Enable contents. So we're talking about minerals. Well, when you take a bunch of minerals and you glom them together, you get a rock. So chapter 3 is about rocks. So rocks are what the earth, the solid earth, is made of. So we're going to talk about the rock cycle, the process by which rocks form, change into other rocks, and are transformed. We'll look at the criteria used to classify igneous rocks and explain how the rate of cooling influences the crystal size of minerals. In fact, is the most important factor in the crystal size of minerals. We'll list and describe the different categories of sedimentary rocks and discuss the processes that change sediment into sedimentary rocks. So we'll go over what a sedimentary rock is and how they form. We'll define metamorphism. We'll explain how metamorphic rocks form and describe the agents of metamorphism, the things that cause metamorphism. We'll distinguish between metallic and non-metallic mineral resources, and we'll look at various examples of each. So Earth is a big system. There's a site, and we can think about this as a cycle by which rocks are formed, change, and are destroyed and such. So the basic cycle starts with magma, molten rock. So magma, it will crystallize either above or below ground to form igneous rock. And igneous rock can be separated into two big categories: stuff that formed above ground and stuff that formed below ground. And they're quite distinct. Because the stuff that formed above ground cooled off very quickly, while the stuff that formed below ground cooled off very slowly. Then, when you have rock on the Earth's surface, it will weather. It will break down into smaller pieces where it can be either chemically or physically, it can be physically broken into smaller pieces, by various forces, or it can be chemically, dissolved or broken down or changed in some way. And then you get sediment, which are solid particles that are produced through weathering. That sediment gets carried somewhere else, usually by water or wind, usually by water. And then it piles up in some place, and it will compact and cement together and crystallize with minerals dissolved in groundwater to form sedimentary rock. If this sounds like concrete, that's because concrete is basically artificial sedimentary rock. And then lastly, metamorphism is that if a rock undergoes high temperatures and pressures below ground, it can transform into a different rock to form a metamorphic rock. So now this is sort of, the process doesn't always follow this path, though. Basically, any type of rock can turn into any other type of rock. So if you start with magma, it will cool and crystallize to form igneous rock. Now that igneous rock might just melt again into magma and form some different igneous rock. Or it could break into pieces, turn into sediment and form sedimentary rock. Or it could be moved somewhere else, undergo metamorphism, and change into a metamorphic rock. Once it breaks into pieces, it forms a sedimentary, and forms any rock, a igneous rock, a metamorphic rock, or a sedimentary rock, can be broken into little pieces to form sediment, which can lithify and form a sedimentary rock. So the sediment can come from any sort of rock. And again, any rock, igneous, sedimentary, or even other metamorphic rocks, can metamorphose to become a metamorphic rock. In fact, there are certain chains of metamorphosis where you get one rock metamorphoses into another, which metamorphoses into a third, and so on. It's like a continuum of metamorphosis. So anything can turn into anything else, but it's a constant cycle. Rocks are constantly changing from one type to another. It's slow, it takes a long time, but that is the process. So this
is Callan Bentley. Welcome back for another smart figure. After watching this video, you should be able to describe the processes that result in each of the different major families of the rock cycle: igneous, metamorphic, and sedimentary. Let's begin our discussion with this figure from the book, which shows examples of igneous, sedimentary, and metamorphic rocks. The textbook is organized according to this order. We're going to begin with igneous rocks, then move on to sedimentary rocks, and finally come to metamorphic rocks. Here's a sample of an igneous rock. It's a vesicular basalt. Basically, the way that this rock type forms is from lava. So what all igneous rocks have in common is that they form from molten rock, either lava if it's above ground or magma if it's below ground. Here's an example of a sandstone. This is a quartz sandstone, such as the one shown in the center image. Sandstone, you may be shocked to learn, comes from sand. And in the case of this middle image in Zion National Park, the structures within the sandstone suggest that it formed in a dune environment. So sand is also present in large concentrations in certain rivers and on beaches, but this seems to be a dune sandstone. Lastly, here's an example of a schist. Schist is a kind of metamorphic rock, such as is found at the bottom of the Grand Canyon, as you see in the bottom center image. And the way schist forms is at the roots of large mountain belts. So when mountains are being thrust upwards into the sky, deep underneath those mountains, the rocks are getting ground around and squished and squeezed and warmed up, and it causes transformations in the rock. So schist is an example of a metamorphic rock. So again, top to bottom, igneous, sedimentary, and metamorphic rocks. This diagram in the textbook describes the rock cycle. Basically, the rock cycle is the collection of processes that result in the different major rock families, the three that we just described. Plus, we've got two sort of hubs on this rock cycle diagram that show sediment and show magma. So let's begin with the molten rock, the magma in the upper left there. If it's underground, molten rock is referred to as magma. If it is above ground, it's referred to as lava. What ends up happening is as it cools down and crystallizes, it produces igneous rock. The igneous rock can come in a couple of different varieties. It can be extrusive if it forms on the surface of the Earth, or intrusive if it forms below the surface of the Earth. But if that igneous rock is then exposed to weathering, so the extrusive igneous rock is already at the surface, but if the intrusive igneous rock is brought to the surface, then it's exposed to the forces of weathering. And basically this means that the rock starts to break down. It turns into sediment, and that sediment is stripped away from its area of origin. It's transported some distance, perhaps down a river system, and then it's dumped somewhere or deposited. And so those deposits of sediment often accumulate in layers, such as is seen in the lower right. Now those layers of sediment can end up getting stuck together by the processes of lithification. Basically the sedimentary grains get packed together, or they get a sort of mineral glue that holds them together, a cement. And so compaction and cementation result in turning the sediment into sedimentary rock. So we've seen igneous rock form and sedimentary rock form. What about the last group, metamorphic rocks? Well, that's where we're headed next. Metamorphism is chemical and physical reorganization of the rock that accompanies higher temperatures and pressures. So when heat and intense pressure are applied to a pre-existing rock, in this case the sedimentary rock, it transforms to become a metamorphic rock. That metamorphic rock itself could then get heated up even further and begin to melt. If it melts, then it's going to produce magma again. So we return to the beginning of our rock cycle diagram here by undergoing the process of melting. Now all the arrows in the middle of this diagram represent alternate pathways, where you could take an igneous rock, for instance, and then you could transform it back into another igneous rock by following that pathway. Or you could take that igneous rock and you could metamorphose it. Or you could take a metamorphic rock and turn it into sediment, and then that sediment could become a sedimentary rock, and then that sedimentary rock could become sediment, and metamorphism could occur to a pre-existing metamorphic rock, and so on and so forth. So the rock cycle actually is fairly complicated if you consider all the different possible pathways a rock could go down. The key thing to get from this is that these purple arrows represent processes. All right, so processes that need to take place in order to transform a rock from one rock type to another. So in the review material at the end of the chapter, you'll find this diagram, which basically shows sediment transformed into sedimentary rock, transformed into magma, transformed into igneous rock. And an exercise that you could go through is to pick any set of characters like these, and then go back to the rock cycle diagram and think about what pathways would have to be followed in order to make that story work. So with our story, we started off with sediment, and then that gets transformed into sedimentary rock, and then we saw melting take place to produce magma, and then cooling of that magma to produce igneous rock. So that was the story we just saw played out on the previous screen. But you could tell a very different story following a different set of arrows here. So maybe for review, ask yourself, what sort of story would I have if I had an igneous rock that then melts and then forms another igneous rock, which then gets metamorphosed? Which sets of arrows would you have to follow to make that work? All right, thank you for your attention. This has been another Smart Figure.
So you don't always have that same pattern. You don't always have that full cycle of igneous, sedimentary, metamorphic. Sometimes the sedimentary rock will melt. Sometimes an igneous rock will get metamorphosed. Sometimes the sedimentary rock will get weathered to form sediment again. Sometimes a metamorphic rock gets weathered. Basically, anything on the surface is going to get weathered. Anything that gets hot enough will melt. Anything that's not quite that hot or is exposed through some other process will metamorphose. So igneous rocks are formed by fire. That's sort of what igneous means. They form as magma cools and crystallizes. And they're rocks formed inside Earth. If they form inside Earth, they're called plutonic, after Pluto, the god of the underworld, or intrusive rocks, intrusive, inside. If they form on the surface, they're formed from lava. So again, molten rock underground is magma. Molten rock, once it's on the surface, is lava. That's the only difference. There are some natural changes that come from it leaving the Earth, in that once it's no longer contained in the Earth, it can do things like release gases stored in it more easily, stuff like that. But if it's underground, it's magma. As soon as it hits the surface, it's lava. In general, lava loses most of its gas because it's exposed at the surface. That gas can just leave, bubble out. It's no longer held in. And these are rocks that form on the surface are called volcanic or extrusive rocks. They're volcanic because they come out of lava from volcanoes, or they're extrusive because they're outside, they're external. They have different physical properties. So in general, they're composed mostly of ions of silicate minerals. The ions are arranged into orderly patterns during cooling. And the longer you have, the more slowly the process occurs, the bigger the crystals that form can get. So the crystal size is determined by the rate of cooling. If you cool very slowly, you get large crystals. So something like granite cooled underground quite slowly, it has large crystals. You can see them in the rock. That's why you see the blotches of different color in like a granite countertop. Each of those is a separate crystal of a different mineral. A fast rate will form microscopic crystals. If you have a piece of basalt, it'll look like a smooth, dark surface because it cooled very quickly. Because most basalt, well, basalt all forms at the surface, but most basalt also forms underwater, cools very quickly. And if it cools real fast, you get glass. So you get things like obsidian. Obsidian is formed when lava cools so fast, it doesn't have time to form crystals. And the way we make glass, like the glass in our windows, which is made of basically, the main ingredient in glass is quartz. You make it from sand. But what you do is you add other things in that basically interfere with the formation of the crystal structure and cause it to not form a crystal structure. So you can make a pure quartz glass. It takes a lot of heat and it's really expensive. But regular glass has various things added in to make it melt at a lower temperature and make it, and glasses in general have stuff added to them so that, that any sort of cooling you would have in the real world is slow enough that is fast enough that it doesn't form crystals. You add things to that interfere, and it becomes a glass. So like the scientific term of a glass is something that is doesn't have a crystal structure. It's a solid without a crystal structure. It's amorphous is the term. And they have different properties because they don't have like a sharp transitions. So they're mostly composed of silicate minerals. There are granitic compositions. These are called felsic. These are ones that are richer in light silicates. These make up things like the continental crust and granite. And then there are basaltic or mafic compositions. These are richer in dark silicates, so they're denser. These make up the oceanic crust and basalts. And the composition is determined primarily by, so there's sort of this mixture of different things. And you can get granitic or felsic, has a lot of these minerals. These are the light colored minerals. Mafic, and even up to ultramafic, has these dark colored minerals. And andesitic is in the middle. And you know, there's coarse grained and fine grained. And the primary thing that determines what type you get is sort of where the magma came from, or the lava. If it came from deep, hot, temperature was a big factor. If it started as very hot, deep magma, you're going to get more mafic. If it was shallower, cooler magma, it's more felsic. Basically, these minerals crystallize out at lower temperatures than these minerals. And we'll go through that. But that is all for today. We'll get back to igneous rocks next time. Let's stop.